Okay, we thought through technical difficulties, and maybe it's actually working. It'd be really cool. I'm really happy to be here. I think are some of the important ideas to get familiar with if you're going to work, generally speaking, with Rydberg physics. And really, this first lecture is devoted entirely to presenting some of the phenomena and basic background you need to understand. Let's go by the generic term, quantum defect theory, generally than that, especially multi-channel quantum defect. I want to try to convey the difference in kind of viewpoints, say, compared to conventional atomic spectroscopy, atomic molecular spectroscopy, where you're more or less going level by level. That's heard about in your coursework, Fock, multi-configuration, ways of identifying individual energy levels, making them in theory more and more accurate, taking into account their interaction with other states. Okay, so anyway, in this first lecture, I'm going to cover these topics, show you where the single channel quantum defect theory came from, and course that has a lot to do with Coulomb wave functions. Some of their properties are crucial to get familiar with at the outset. And then what is likely to be less familiar to most of you, because most of the world really are familiar with this, probably not taught very often. What happens if you have Rydberg series converging to multiple ionization thresholds, which lead to a whole class of really interesting, including, of course, ionization being one of them. And then there's the more general phenomena I like to call complex resonance, where it's not that useful to just think like where you have a single bounce, where in the case of complex resonances, we'll see multiple times multiple energy scales coming from, which makes the spectrum look really great. And by the way, I put a link here. Maybe if any of you can't read it or don't have a way to jot it down right now, send me an email. This basically has, right at the moment, my first two lectures, the PDF forms. It also has some Mathematica notebooks that I wanted to give you example calculations. You can use yourself. And there's also, if you don't have Mathematica, system, there's a PDF printout of it, and at least trace through the logic. Pretty easy. So most of what I want to do is let's start, and as usual, let's work in atomic units. For E, H bar, radius, or one, structure constant, 7 units. So the simplest situation, the simplest scenario, think about single channel quantum defect theory, is you just have a radial Schrodinger equation. And I like to do the rescaling by little r times the actual radial capital R, because then you get only a simpler form of the kinetic energy operator with first derivative terms. You get a centrifugal term, of course, L squared. And
outermost electron. Coulomb potential minus 1 over R, and then there is a shorter range screening potential, essentially, especially closed shell ion, alkali atoms. Then there will be a strictly symmetry screening potential that represents the effect of and then of course there's the energy E, which will often represent within effective quantum energy scale. So the effective potential we're talking about looks something like this. Centrifugal potential. If there is L non-zero, you'll have a centrifugal area, of course. But basically, the potential looks Coulombic at large enough distances, and it deviates from the Coulomb, the Coulomb being the dashed blue curve in this figure. Any screening causes it to be more attractive at the origin, and eventually, when you're close to R equals 0, you will see the screening of their potential with the full chart. Yeah. Sodium. So you can imagine sort of solving the Schrodinger equation in line. You get the Boyle waves, some E I've drawn here is positive. And we know just the way you do in scattering theory with zero potential inside of some radiant matching radius where potential is vanished. If there were no Coulomb field, then these would be a linear combination of spherical Bessel functions. These F and G, basically all the magical practice would carry over to that. So you have scattering phase shift delta L that reflect the superposition of the regular Coulomb function, which is down, and the irregular Coulomb function, which is G, at all distances where this Bs of R is negligible. That's and it'll be something complicated. We can't generally solve it at small distance. But a lot of the beauty of quantum defect theory is that the sort of hard work of solving the Schrodinger equation, the part of it, is all restricted to this small volume, and all the rest from R naught going to be completely done. So that was one key point about the analytic solution. The second key point is that in the classically allowed region, say I've drawn energy here, just below the ionization threshold, you can kind of imagine the electron can tell from its de Broglie wavelength that it's at this point it just oscillates just like it's positive energy. That's the turning point. It says, "Oh darn, I have to go back because I can't." And so you'll get standing waves, certain energies, and quantized energy. The third key point here, which is also goes by the name of Seaton's theorem, is that the scattering phase shifts, they really vary quite slowly with energy. If there was zero long-range potential, like electrons got neutral, there's no Coulomb potential, you know, there would be things like the Wigner threshold law, fairly fast energy dependence on the phase shift. But in the Coulomb field, for the reason the phase shift goes quite smoothly to pressure and even to below. And when you're below threshold, the scattering phase shift is what tells you the energies of the bounds. This is also known as Seaton's theorem, which I've written down here. I think the sketch of the derivation of it in a minute. But basically, delta L of E ends up being rewritten
And then UL, which is weakly energy dependent, controls the Rydberg energy bound states of this portion of this or if it's an atom with strong spin orbit interaction, also have a J attached. So here's how the basic derivation goes that you would find by important review article from the early 1980s. That the regular function, you can just look up the asymptotic form of these regular Coulomb functions. There is exponential growth and exponential decay, as you might expect. And of course, the exponential growth is totally unacceptable. You can't have that at infinity. And one interesting thing about quantum defect theory is it works a lot with functions that would formally be infinite at infinity for almost the entire calculation. That might seem like a bug, but it's actually a benefit because you get smoother energy. And the very final step of any quantum defect calculation is killing off all the exponentials. So it is always rectified at the end, but you get smoother quantities by working with these exponentially growing terms, which essentially have disabled the electron from turning around the classical turning points. It's as though it can go right through and not make back reflected waves that have very fast energy. So F looks like a sine of pi times the effective quantity minus pretty much ignore in these formulas. The most important thing is the exponential part, the rising part of F has sine pi now, and the exponential rising part of G looks like negative cosine. So when I put that together with the phase shift, I get the entire coefficient of the exponential term that needs to be made zero in order to have a bound state. And that's then wait the argument of the sine function. This gives the quantization formula. The effective quantum numbers, in essence, the denominator of the Rydberg formula, have to be an integer n so minus the quantity. In many problems, you can treat mu quantum defect in some cases. They're really very, very high precision. You'll see some fit this to a quadratic function. For most purposes, a lot of people here are doing experiments on very high Rydberg state. Okay, so these are the two main points I already mentioned. Slowly with energy from bound states. Same quantum defect taking the positive energy tells you scattering phase shifts you would need to find the distribution of an electron scattering off of this ion core. Kind of philosophical aspect of QDT is sort of viewed as solving the Schrodinger equation outward from the origin. Initially, you can just pick any energy, even if you don't have a bound state, and find this smooth information. Then you can only need to apply that large power boundary condition. So the very last step. And this was the point I mentioned about laying the imposition of large boundary condition is a major reason why everything is so smooth. This is a demonstration from that notebook showing a positive negative energy solution. So points are positive energies, regular and irregular, and the solid curve is a negative energy solution. So if that's negative energy, it's lower energy because there's more. You see at small distances out there, these are almost normally one thinks qualitatively totally different versus bounds. It shows the interconnection between scattering states and bound states. You do much work in quantum defect theory, you need to get familiar with forms of the regular and irregular solutions. One annoying thing compared to Bessel functions is they have this logarithmic argument, and then so you have to know so accumulating that logarithmic phase all the way to infinity. There's also this eta, which contains part of it, Coulomb phase shift. That comes in lots of scattering, photo ionization, angular distribution. This is an example of the smoothness where they take experimental energy levels and turn them. The integer part of quantum defects is usually not important because the trig function is effective. You can see that the non-integer part of the quantum defect goes and it equals 6. 60 is and this is a graph of what versus flattens out, becomes virtually constant. Yeah. One other thing I might mention is we call the functions f, like f and g, we call those energy normalized, negative energy Coulomb. That might seem confusing. Normally you have to integrate to energy normalize a continuum. And of course, F and G would diverge. So large and negative energy, they would diverge. But we call these energy normalized anyway because they are the smooth of the positive energy. And we work a lot with these, and these are the ones that affect most smoothly to positive energy. Then when you want to make a bound state normalized negative energy, after you've done the discretization, found the effective Hall numbers where the state is found, has no exponential growth, you can divide by the normalization. Root of the normalization constant, which is nu q. And again, this is derived in C. This is showing a few more properties of these things, like in the Mathematica notebook, I gave you an example how you can calculate the quantum defects of sort of crudely optimized S of R that I earlier. And you can just integrate the Schrodinger equation out to 15 radii, match tiny phase shift on defect. And this is smooth curve. Points instead came from maybe a more conventional way of finding bounds. Big basis. Diagonalize the Hamiltonian, and you see there's quite good agreement. There's higher where you started to run out convergence regions. This graph on the right shows at one radius, the regular function, irregular function. It's not just continuous at 0. Yeah, I also this was a this bottom left figure where the quantum defect scale is so tiny. This is for and this is an important thing to realize also that the centrifugal barrier keeps you outside of the region where PS is reachable. Then of course you'll have very tiny part that gets into small distance. Will create a quantum defect that and any longer such as the polarization. Sodium plus iron has and that determines most quantum defect theory is mostly unnecessary for partial waves higher than 2 or 3 quantum defects. And you can just use hydrogen. So now let's take the next step to multi-channel physics. So I think most of you are less likely to be familiar. So what we're imagining now is these two purple horizontal lines are 2 ionization thresholds. This is a very common situation, for instance, in basically almost every atom in the periodic table with a closed shell core are going to have these multiple ionization thresholds. Now there are the first thing you should think about thinking of the multi-channel Rydberg physics of any atom is where are the ionization thresholds? Because everyone is guaranteed to have an infinity of Rydberg levels attached to it. So here I've drawn a couple of Rydberg series attached to these two thresholds. And we can start to imagine all the physics that happens. And there are basically 3 different energy ranges where the physics is quantum. So I should also say there's not, in general, just going to be one Rydberg series attached to it, because all the partial waves of the outer electron are also present. So it's really, there will be infinity attached to each thing. And I just say pick one symmetry and I pick one Rydberg series. So in the open continuum, that's the highest energy range, called the open continuum. And if there are no other sort of you don't normally expect there to be any resonances happening. If an electron comes into the ion and this energy of E2 scatter, it could either excite the ion from E1 to or de-excite or it could elastically scatter. Basically, there would be a 2-channel. Of course, you have no closed channels. The solutions have no exponential growth or decay. Still represent the full solution in this general form. beta independent solutions at every energy. The beta independent solution is an anti-symmetrization of this ITAMP, which is a wave function, and combined with any angular momentum or spin functions of the Rydberg electron, the outermost electron. And then you have F minus G with coefficients. These are each 2 by 2 matrices in general, I, J. This form is kind of a starting point for thinking about what's going on. And I think when I was first learning MQDT, this was maybe the hardest thing for me to get in my head. Why are there more than one solution in the Schrodinger? In hindsight, I shouldn't have been confused by that because you know that you only go to channels that you have to have an S matrix. It has to be a 2 by 2 S matrix, and each column of the S matrix represents a different independent solution of the Schrodinger equation. So you have to get used to this fact that however many channels are in the problem have to be the dimension of your S matrix, and sometimes it's recast as a real reaction matrix, K matrix it's called, or you'll hear the R matrix. They are constants, however. They have no R dependence, as you're in the region where the potential is purely Coulomb once you're beyond matching ranges, where it's Coulomb. It's not. Important thing to realize, though, is because these are two linearly independent solutions of Schrodinger equation, any linear combination will also be. And so the idea is use that fact and choose the constant C beta to satisfy the appropriate large value. So, for example, in this point 4, your goal is to describe a scattering process for an electron. Then what you would do is you would make a scattering wave function like C beta so that psi has an incoming wave, unit normalized first channel, and you'll find it has outgoing waves in both. The coefficient in front of those will be exponents for the elastic scattering or inelastic. We were talking before about F and G, but to do scattering calculations, use the outgoing and incoming plus. So then you can rewrite that same solution I had before in terms of that, where you see explicitly the outgoing wave by J and the incoming wave multiplied by its conjugate. And so from this, we see that to make this wave function we were talking about, where you're incident in just channel I prime, you would have to multiply by the matrix C beta I prime, which is the inverse of capital the inverse of that matrix, beta I prime. And do that matrix vector multiplication. That would give you that scattering solution in the open continuum. It's a little bit of a boring region, unless you measure that inelastic scattering process. You have no resonance expense. Okay, so once you've done that, you'll have this form of your solution. We often write as psi plus, the scattering solution, with outgoing waves having amplitude SI. Channel. I prime again, it's the incident channel. So you see the conic delta function delta, which is telling you that that's the wave here. And the probability will be epsilon. And now you put in the kinematic factors, flux, and so on, and calculate collision cross sections. So this would all look like standard scattering theory here pictorially. I often like to draw these as motion on potentials. Even though we have a time independent solution, we can think heuristically that a wave packet would be coming in let's say on the lower channel with incident only on the lower channel. When it collides with the reaction volume or the ion cores and all that physics of the electron ion interaction, then you can come out either in the same channel and go off to infinity or in the upper channel. Once you're outside the box, you'll stay in that whatever potential you're in until you yeah. So again, just to sound a bit like a broken record, this final comment on this slide, the power of MQBT is going to come from realizing that these solutions, either the ones I wrote before in terms of F and G, or these I've written in terms of F plus and F minus, these are all smooth, and we can analytically continue to make the energy very smooth. So these same matrices, like S, continues analytically. So that allows us to treat with this all the information we just learned by solving the continuum part. We can treat the optimization. What's different is that now at this energy between the thresholds, one channel is channel two. So we know to expect exponential growth as R goes to infinity. So now the linear combination we've got to find is all that exponential growth. We can do that by looking at the wave function. We know the electron could not escape to infinity. Maximum distance of the wave function physically decays exponentially. So one maybe useful step is to go to the K matrix, the reaction matrix solution. We often prefer to work with this because K is a real symmetric. And then you can do this whole calculation with real functions. Now you'll have to take a linear combination of these two independent solutions, Ci prime, such that you'll get exponential K in channel 2. That can be done, as I said, algebraically. Just plug in the forms of F2 and G2, see their exponential growth. And when you plug that in, it'll spare you detailed algebra. It's pretty straightforward. You'll need this equation to be satisfied in order to kill the exponential growth. That tells you how C2 and C1 are going to be related. And then that in turn tells you that there will be, after plugging that in, you'll only have functions that can go to infinity in channel 1. They will have what we now call the physical kingdom, which is reduced because channel 2 was eliminated in the sense that its exponential growth was eliminated, but also its dimensionality was eliminated. And we just get a phase. This would be like the tangent of a phase shift in the only open channel. You will still have the part of the wave function that's exponentially decaying. Sometimes you need that. But this is one of the important formulas of MQBT, that this physical reaction matrix takes the smooth elements of K and combines with the inverse of this tangent pi u plus K22 times the K12 and K21 elements. This shows you where all the resonances are going to be every time you go through one quantum number unit in the quantum number to the upper channel. you're guaranteed to have a resonance. You're going to have a high rise of the physical quantum defect for channel 1. So you get all these resonances and infinity, in fact, resonances between channel threshold 1 and threshold 2, and of course they show up in scattering theory or in photoabsorption theory. Photoabsorption, you'll often have to calculate the dipole matrix element. There's a similar formula this, where you write sort of a Feshbach projection language, P for the open channels, Q for all the closed channels, and then in that partition matrix formula, you see the physical dipole matrix elements to the K matrix states have this resonating tangent pi nu in the closed channels. Whenever that determinant of that matrix is 0, you get resonances, huge, often enhancements in cross sections, and then there's cross section formula. Too many details of that, except that you see the structure, how you're going to see whenever the physical K matrix resonates, whenever this matrix has 0 determinant, goes to 0 determinant in physics. So let's look at some examples that I took there in this mathematical notebook. You can set the smooth dipole elements, those are dk, and the K matrix. Different cases. This first one here, upper left, is a fairly typical one where the continuum channel and the discrete and closed channel have comparable amplitudes. Then you get some asymmetry in the resonances, and with fairly large off-diagonal elements in the K matrix, you get very broad. If you change that situation to a case like this, where the closed channel has a very small dipole element, you can see that there is only a very very small coupling in the K matrix. You get very narrow resonances, like symmetric, like you expect for funnel line shapes, and basically, except over very narrow energy ranges, the cross section is the same as it would be if there were only one open channel and there were no resonances. In a lot of fields, some situations in AMO physics, and a lot of very common situations in nuclear physics, the closed channel resonances dominate the spectrum. That's really where you see huge resonance effects. This set of amplitudes with a large closed channel dipole and a very small open channel dipole would reflect that situation. And now you see a very tiny continuum cross-section background, but very big, huge spikes at the resonance energies. And that's typical closed channel. Before quantum defect theory was developed, you would maybe pick one of these resonances and fit it to a funnel line shape. Famous article characterizing autoionization line shapes by this formula. Asymmetry funnel line shape parameter Q, polysymmetry resonances with resonance. Now with quantum defect theory, you don't just get the one resonance. You see the pattern. A couple of other observations. If there is just one continuum, then one interesting thing about funnel resonances is that there will always be one point where the cross section is property if there is only one continuum. Another thing is, as Fallon showed in his paper, the scattering phase shift will rise by pi across the resonance. And in a paper with Pfeiffer's group, if you're interested, in Science magazine in 2013, we discussed that there are time domain implications. If you do a pulse excitation, you can relate this quantum Q parameter to a phase delay in dipole response. The only other energy range in this two-channel problem I haven't discussed yet is this one, where both channels are close. So we went down from open continuum to auto-ionization between the thresholds. If I go below both thresholds, both ionization thresholds, there is no continuum in the problem. You either have at any given energy either no state whatsoever or a balanced state. So what you're usually interested in is the bound state energy. These can be computed in the form of a Lufano plot, where you can plot the quantum defect relative to the lower threshold in this case, as a function of the effective quantum number. Lufano, notice that this figure tends to look quite periodic. Every time nu2 increases by 1, you get the exact same shape of this continuous curve. Calculate the quantum defect continuously. The only bound states happen at these points, but the curve you can calculate continuously in energy. So Lufano noticed this periodicity and pointed out that you could then collapse this figure and do the upper channel modulo 1 and the quantum defect modulo 1 and collapse all these periodic cycles into a single graph. So sometimes you'll see, like in this 1973, you'll see this collapsing periodicity. You can much group the entire spectrum. These are some examples from out. You see the rise in pi. In this case, like in calcium single Fiat, it's because there's a 3D 4P virtual. The two channels have the threshold of 3D, threshold of calcium. And the 3D character gets distributed among several Rydberg states. That's one thing I like about these kind of graphs. Is you don't just see one energy level, especially in this pattern construction. Okay. The final subject I want to talk about is the complex resonance. Okay, so we went from one channel to two channel. Now we introduce one third channel. We have this I'm talking about here, so-called complex resonance, requires at least 3 thresholds. So now again, you can think big picture. You're going to have Rydberg series, at least one. So there are 3 Rydberg series somehow interact multiple times. In Tillman's talk, he mentioned the Kepler frequency. So basically, if I pick an energy, this energy that's attached to it. If I pick this energy, there are 3 time scales. There's the time scale associated with motion in chapter 1. There's the Kepler frequency in chapter 2, and a different Kepler frequency in 3. It's basically nu q, period, 2 pi. So you can kind of imagine that, like if we say dashed energy, there is some physics very, very slow in channel 2, because you're at a very high effective quantum number in channel 2. You're at a much lower in channel 3. So you're zipping in now in channel 3. For this complex resonance scenario, I'm mostly interested in this region between channel 2 and 1. And again, this is unit for energies and atomic units. This is the formula for each effective point. So there will be a 3 by 3 K matrix. That's the smooth point. And if we know that, let's assume we know that, then we can solve for the physics in this region, regions 1 and 2, by first eliminating channel 3. First, just eliminate exponential growth in channel 3. That brings us to a 2 by 2 K, where all the elements feel that inverted tangent pi nu plus K through 3. That shows up as a denominator term, and every element now is reduced 2 by 2 matrix element. So this is no longer so smooth with energy. This will resonate every time you go through a resonance in the third channel. Positive balance in the third channel. And you have a similar elimination. So now you can put that together and eliminate the final channel, the exponential growth in the final channel. Now there's only one open channel, and that gives a 1 by 1 physical, what I call physical, which I can also call tangent, which now feels the resonances of channel 2 as well as the fact that K tilde feel the resonances from channel 3. Now, the rest of the formulas are the same as the 2 channel, except they're energy dependent. This is now the type of spectrum where you not only have the very, very periodic Rydberg states going to the second threshold, you can see a huge modulation when you go through the energy of the state going to the third threshold. And there are a lot of interesting things that happen here. One is that the individual funnel light-shaped cube parameters that play the symmetry, they change sign as they go from the left of that complex resonance to the right. See, the rise is steepest after the minimum on the right, before the minimum for the individual funnel. Another interesting thing is there will always be one resonance of these fine individual resonances. So this modulates not only the intensity, but also modulates the width, right? Interestingly, you can make this smooth curve that traces out the width of these individuals. And that itself shows a funnel width. And the final possibility we discussed in this 1992 paper is you could have the energy levels of the thresholds dependent on a parameter. Now you could see, as like a magnetic field or something, you can see the complex resonance sweeping through and affecting these fine resonances in the weaker level. So there are a lot of examples of this in literature. This is a pretty famous one that I the Brown and Genter experiment on strontium photoionization, where you see the fine Rydberg states. And you see an asymmetrical complex resonance that modulates all those frequencies. Our matrix theory, developed by Mary and some of those papers explain this theory very well. There were some really impressive cases done by Christian Jungen in the hydrogen molecule, where you have many row vibrational thresholds, and you get complex resonances all over. It's not much detail. But this HP example that we were involved in was measured in Frederick Merck's group. Top was experiment. Theory was the prediction. Image. You see this complex resonance, which is modulated again. So the last case I want to show you is both an old story and one that's recently found renewed interest. A different way of exciting most of the experiments I was telling you about before, you have a very low state or a ground state absorbing the photon up to the energy range of these systems. Now, there's this alternative studied a lot beginning in the 1980s, where you first start, you take your ground state out of the area, and 1 or 2 laser photons get up to the Rydberg states that are bound. 6s and S states. And now you've got that electron in this Rydberg state just hanging around, and you can bring in a laser that's tuned to the resonance of the ion. It will take the 6s state of the inner electron up to the state of the core. This is called the isolated core excitation, where that final photon absorbed is actually driving the inner electron. You can't see this phenomenon. There's some 2 valence electrons. You can see this all the time. And now something interesting happens. You can write the dipole matrix element for this process as the product of the ion dipole. 6p, in this case 6p1. But the outer electron has to shake off from its original 6s ms state into the different s states. So there is an overlap in nu s to nu prime s. And nu prime will be a function of energy. Nu s is fixed by these first 2 factors. And that overlap function affects the shape of the spectrum. This is the type of spectrum you get. There's usually a main line where the effective quantum numbers are approximately equal bound to the off-ionizing state. But because the Rydberg states are orthogonal, the S states are orthogonal, you get these deep cut zeros in that function. And every time you go in one effective quantum number away from this deep. This overlap factor is known analytically. You can see from this sign function where those zeros in the spectrum. So there's a very recent application Burgers, Thompson, where they made use of this spectrum for some of their quantum control, quantum information-oriented experiments in the following way. That they are interested in applying a light shift to Rydberg states to shift those states in or out of the spectrum. But of course, if you bring in a photon to do that, it's near resonance. It's going to likely take you up to the auto-ionization and you can destroy your Rydberg. But they notice the following, that because of the nature of this isolated core excitation spectrum, well, if I park my laser right here, then yeah, I have a lot of light shift, but I'll have a lot of auto-ionization. This is the basically auto-ionization. On the other hand, if I go to one of those zeros, sign range, then I get almost no photoionization happening. You're going to very close to zero. Nevertheless, the light shift stays quite constant. So by tuning to one of these shifted lines that have the zero in the overlap function, they can achieve their light shift without causing much, which is the Rydberg happens. There's a very similar story that was published, submitted almost the same time as So it's an example of how knowing some of this properties of these multi-channel Rydberg systems, you can do some tricks in this field that can be useful for those of you who are more interested in the. This is all the math. It's all pretty straightforward and laid out in the appendix. You need to keep track of amplitudes of those exponentially done. Do this sort of calculation. That all comes out. And then Kromers-Kronig type formula for the light shift. Just one last slide showing that the fit we had before, that's this blue curve. This was basically where we started when we began Princeton group, because there were no first principles calculations of the spectrum in this energy. But with Miguel, we later were able to get our do a 2-electron first principles calculation, and you see it largely agrees with the MQ fit, which is artificially restricted to very few channels because we had only really this data to try to fit. And you see it basically largely agrees, but it kind of got rid of these there that happen to be between the data points. We didn't really have data in that energy. So in some cases, you're stuck with trying to fit these K-matrix elements. In other cases, you can sometimes calculate the first principles. But in any case, I think it's a really useful tool, especially work with atoms more complex than alpha. For this section. Complex resonance you're talking about? Okay, yeah, like in this picture, you can see some time scales. Of course, here is the, in channel 2, this is the Rydberg space. It's 2 pi nu cubed. It's that frequency. There is the quantization widths of the individual features, which change across the complex. Those are actually all different as you go through this. The Kepler period of the third channel would be the distance from this to the next. This big blob, where is the next one? That would be the fast frequency in channel 3. And then finally, there is this width of the whole, just this one. This would be the autoionization width if channel 2 were open. Channel 2 is closed, so that's essentially telling you the time scale for the electron if it is in this complex resonance for it to decay to either channel 2 or mostly channel 2. those are the different types of things. Yeah, um, so in all the two valence electron systems, it's pretty straightforward now to do the calculation. For a lot of atoms where it's more channels or it's more than two electrons outside the closed shell, people have tabulated the K interested in rare gases near those thresholds, like the J goes on up, people fitted to the spectrum before there were calculations. But when you're approaching a whole new system, and experimentally, you may not have the ability to do it. Channels, the number of channels is not too large. You can try to fit the which is how it's but for instance, in ground state photoionization of barium, this could only be tackled by fitting in the early 1980s. We've got a 13 channel canvas. It's pretty hard to get data to give a really variable leader fit. If you have more than 5 so that's one limitation. If you have more than 5 channels, pretty much better finding some way to or get a whole lot of data. Very many different. Princeton experiment. The ab initio calculation, I think this was about a 13. The limited data we had from the Princeton group. Two different symmetries, one with 2 channels and one with 3 channels. Right, like that. Rubidium is a different formula. Well, that would be threshold. Well, I would say also actually my next lecture, which will be let's say you have hyperfine split thresholds. Quantity factor sees say from zero spin isotope. Go to a non-zero thresholds. Francis. Some right. we have to do some fitting, and we collaborated with Francesca for them. A lot of their spectrum from their day. Well beyond.